Alright guys, welcome to Unit 2. Unit 2 is all about dynamics and forces, as well as Newton. Newton is a very prominent guy in this video, because, this video is really all about his laws of motion that he made, so, kind of be expected. Last unit we talked about kinematics, which is basically kind of how things move, right? We looked at UAM, like things like time in air, velocity, acceleration, displacement. This video, instead of looking at how they move, we kind of think more about why things move. Now, this answer is kind of intuitive. Oh, when you push on something, when you apply a force to it, it's going to move. Wow, who would have guessed? But these kinds of like this intuition, it's formalized in Newton's three laws of motion. These three laws are fairly important in this course. Actually, no, not fairly important. They're really important, I'd say. And he technically has a fourth, his Newton's law of universal gravitation. I'll get into that at the end of the video, but it's not too important. You don't need to try to memorize that yet. Yet, of course. It's more prevalent in later units. Yeah, no, I'll just get into that at the end of the video. But this video, I'm not gonna be using the screen too much. It's gonna be mostly me just blabbering. But I will use it occasionally. Anyway, I'm gonna get into this here. Newton's first law is sometimes called the law of inertia. It basically just states that unless there's an unbalanced net force, an object at rest will remain at rest, and an object in motion will continue to move at a constant speed. Now, basically, this is saying that an object will maintain its state of motion unless acted on by an unbalanced net force. State of motion being whether it's at rest or not at rest, right? For example, if I'm staying still and I don't do anything and no forces act on me, or at least no unbalanced net force acts on me, then I will just stay completely still because I'm staying at rest. My state of motion isn't changing. If I'm moving along a conveyor belt at a constant speed and no external forces occur, like maybe who knows, maybe like if I don't get like shoved by someone, if there's no absurd wind, then I'm gonna keep moving on that conveyor belt at a constant speed unless the conveyor belt changes its speed for some reason. Don't know why a conveyor belt would do that, but you never know. Uh, anyway, next is Newton's second law. Newton's second law just states that the sum of the forces is equal to the mass times the acceleration. Technically, I'm pretty sure Newton, when he first composed this law, he stated that the acceleration was proportional to the force, and the acceleration was proportional to the inverse of the mass. So then this could be stated as acceleration is equal to force over the mass. This can just be rewritten as F is equal to ma. But like I said, it's the sum of the forces or the net force, and that's indicated by the sigma. I'm pretty sure it comes from Greek letters. I think it's a sigma. I don't know actually, but that symbol just indicates like a net or like a sum. Do note that the force and the acceleration have to point in the same direction. Both of these are vector values, and they point in the same direction. If the net force points towards the right, then this object is gonna be accelerating towards the right. If this object is accelerating towards the left, then the net force is pointing in the left direction. This ties in with Newton's first law actually quite well. If there's an unbalanced net force, actually no. If there is no unbalanced net force, then that means the acceleration has to be zero by using Newton's second law, right? No net force, then that side's equal to zero, so then zero equals ma. That means a has to be zero because mass isn't zero. And when acceleration is equal to zero, velocity doesn't change. So then it maintains a state of motion. It will either continue to move at a constant speed or it will stay at rest, right? Newton's third law is kind of the opposite, equal and opposite. You might have heard this before, but it just states that for every action, there is an equal and opposite reaction. This works well in the context of forces. For example, here, if I have an object A and object B. If A is pushing on B, then A is exerting a force toward the right, right? Right. But B is exerting a force back on A. However, this force is in the opposite direction. A pushes towards the right, so then B pushes towards the left. These forces, though, are of equal magnitude, meaning their relative strengths are the same. Now, like I said, I will get into Newton's law of universal gravitation. Basically, it just states that any two objects will have a gravitational acceleration between them. Actually, no, a force of gravity, a gravitational force between them, basically. This can be modeled mathematically with this mess. Now, like I said, you don't need to try to memorize this yet. This becomes more prevalent in later units, especially the unit on circular motion and gravitation. After all, the unit's called gravitation. You would expect an equation about gravity to be prevalent in that unit. This unit, though, we don't care too much about this force of gravity equation because it, like, most of the time when we're thinking in unit 2, we're thinking we're on one planet where the gravitational acceleration is constant. It doesn't change. This equation is only used when the gravitational acceleration is not constant. So, yeah. Anyway, yeah, no, that's it for this video. Next video we're gonna talk about free body diagrams and types of forces. Free body diagrams are quite useful for being able to accurately use Newton's second law, and we want to be able to draw an accurate free body diagram. And to do that, we would like to know types of forces. Yeah, I'll see you next video.